See, there were 4 requests for me to work out DrC problem number 2 from homework number 1. So let's go ahead and do that. Now, a picture was given in the problem. So let me draw the picture as I remind you what the problem says. You have a car that's initially stopped at the traffic light, but remember this is a one-dimensional system, so I'll start off by just indicating what my x-axis is and my origin, and the origin will be the traffic light. And there's a car stopped there, so I'll draw a little dot for the car. The front of the car stopped at the traffic light, and that's at t equals 0. And the light turns green at t equals 0, and the car starts moving with constant acceleration. So I'll label that the acceleration of the car, a sub c, equals 2 meters per second squared. At the same instance, the front of a truck, so I'll mark a truck with a bigger circle like I did in the drawing, truck, car. The truck is traveling at a constant speed, v sub truck equals 15 meters per second. It passes the front of the car, and the car is initially moving at 0 speed, so the truck gets ahead of it. But since the car is accelerating and the truck isn't, then the car will eventually catch up and pass the truck. Okay, so how are we going to approach this? You're told, by the way, that the position is defined as x equals 0, and you're asked for what's the time and what's the distance, x equals d, where the truck or the car eventually catches up to the truck. Okay, so part A says calculate the values for t, d, and d, and provide a symbolic answer first before you plug in numerical values. So the equation of motion, remember the general equation of motion for something in the x direction is x equals x naught plus v naught t, where v naught's in the x direction, but back at the time of this homework, we're only considering one-dimensional problems. So plus v naught t plus 1/2 at squared. So that's the general equation for motion. And what we know then is if you apply this to the truck will just be x sub t equals v sub t times the time, because the initial position of the truck, x naught, is 0, and the truck has no acceleration. So that's a simple equation. That's true because the initial position of the truck equals 0, and the initial velocity, or the truck velocity's original, equals just a constant, and the acceleration of the truck equals 0. How about for the car? For the car, its position is just 1/2 ac t squared. And that's true because the initial position of the car, x sub c naught or not c, doesn't really matter, its position is also 0. It stopped at the traffic light. And the original velocity of the car is 0. So these two terms are gone for the car. You're just left with 1/2 its acceleration t squared. So what does it mean for the car to catch up to the truck? Well, that just means they have the same position. So at that time, at t equals td, at the time when they catch up to each other, are ready to pass, the position of the car equals the position of the truck, which is d, the value we're after. What's the position? So we just set these two terms equal to each other and say, let's solve for the time when the velocity of the truck times the time is equal to 1/2 the acceleration of the car, td squared. And we want to solve this for td. That's one of the things we're after. Just do a little bit of algebra, and you see td is equal to 2 times the velocity of the truck divided by the acceleration of the car. Okay, remember what I'm doing is canceling out this squared with that, and then just solving for this td by multiplying both sides by 2 over a sub c. Okay, then I can plug in the values. Now that I have a symbolic formula, 2 times 15 meters per second times 2 meters divided by 2 meters per second squared, the acceleration, and the 2's cancel, and I'm just left with 15. The meters cancel. This second cancels that, and we have 1 over seconds, and so that's just seconds. So the units work out. That's good. Gives me more confidence in my result. So that's the time we're after. How about the position? Well, the position can be found from either of these two equations. Take your pick, but this one's simpler, so I'm going to pick that one. So x sub truck is the distance, equals the velocity of the truck times the time that we just solved for, or 15 meters per second, times 15 seconds, or 225 meters. And you'll get exactly the same answer if you plug into this equation and use the acceleration of the car times the same time. So those are the first two things we were asked for. Part B says, what's the speed of the car when it catches the truck? Here we can say that the velocity of the truck equals the acceleration times the time. Plus V naught is 0, so we don't have to worry about that. And we can just plug in the values, 2 meters per second squared times 15 seconds. That's equal to 30 meters per second. Okay. And finally, we're asked in part C, what is the average speed, or it actually says which vehicle has the higher average speed during this time interval. Doesn't actually have to solve for anything, but let me just remind you that V average equals delta x over delta t, and what we know is that delta x is the same. They've both moved the same distance from the traffic light to the point where they pass each other, and so if it's the same for both, then neither one has the higher average speed. They both have the same average speed. And if you want to work out the value, that'll just be the distance they've traveled, 225 meters from part A, and they've done that in 15 seconds, and that's 15 meters per second. Done.